Hello folks, today in this video we're going to talk about projectile motion, which is the motion of an object in multiple dimensions. Let's get started. So when we're dealing with objects that are moving in multiple dimensions, like 2 dimensions here where you have a ball rolling on a table, we can consider each of those dimensions separately. In fact, it's almost as if you can completely ignore the one dimension when you're looking at another dimension. The really neat example of this is the question about a bullet fired versus a bullet dropped. If you take a gun and were to fire it straight forward and at the same time drop a bullet from the exact same height, both of those bullets would hit the ground at the same time. And that's due to the independence of motion, that the motion of a ball, let's say you have a ball rolling off of a table like this, the motion up and down does not affect the motion side to side. And so we only need to consider what would happen to an object falling to consider the up and down motion, and then we can consider an object going forward when we consider the x direction or horizontal motion. So each dimension can be considered separately. Now there's a lot of different problems that you can ask, but we're going to kind of split things up into two broad categories. The first one I'm going to call horizontal projectiles, and then we've also got projectiles where you have vertical motion going on as well. So here we have a ball launched from the top of a 42-meter building with a horizontal velocity of 32 meters per second. There's many questions we could ask, but probably the first one that you might ask is, well, how long is the ball in the air? Now, there are many ways to start tackling this, but one thing I like to do is be organized, because we're going to start dealing with things in multiple dimensions. So each of our variables applies in both. So I'm going to kind of keep a list over here. I'm going to keep a list of our horizontal things in an X column. I'm going to keep a list of the vertical information in a column labeled Y. So when we say this building is 42 meters high, that is going to be the distance in the X direction. And so I'm going to say, in the Y direction, I apologize. This height, of course, is in the vertical direction. So that's the distance in my Y direction, 42 meters. When it says that the horizontal velocity is 32 meters per second, that's telling me that the initial X velocity is 32 meters per second, because that, of course, is in the horizontal direction. Now, is there any other information they've given me, or is it just those two numbers? Now, remember all of the variables we could have. We could have our final velocity, we could have acceleration, and of course, we have the time. Well, I always know if an object is in free fall, if it's falling on Earth, that its acceleration is 9.81 meters per second squared. And that's always going to be in the vertical or Y direction, because of course we know gravity acts downward toward the center of the Earth. And so that's going to be my acceleration in the vertical direction. Because of that, is there any acceleration in the X direction? Well, no, of course not. There's nothing pushing or pulling my ball forward or backward. There is no X acceleration. And so we're going to say the X acceleration is 0. And you're going to find that to be very true often in these types of problems. Similarly, I know my ball is moving with a horizontal velocity. What's the vertical velocity then? Is it moving up and down? The answer is no, it's just rolling along the top of the building. And so we can say that its Y initial velocity is 0. Okay, now we have some information that we can start with. So the first question we're going to ask ourselves is, how long is the ball in the air? Well, to answer that, we can use either the X direction or the Y direction, because the time is the only thing that is going to be the same in both directions, which makes sense because it can't fall longer than it goes further out, right? It has to be the exact same time. It hits the ground when it hits the ground. So we can use either direction. I'm going to use the Y direction because I know 3 pieces of information. I know the distance, I know the initial velocity, and I know the acceleration. So go ahead and take a look, find an equation that includes those 3 variables, and you could use to solve for the time. What you'll find is I would use this equation, that the change in position, the distance, is equal to initial velocity times time plus 1/2 acceleration times time squared. So from here, I'm going to plug in my numbers. 42 meters is my change in position, my distance. That equals, here, my initial velocity is 0. So it's all just 1/2 times the acceleration, 9.81 meters per second squared. Oh, no square there. And then times the time, which is t squared here. Get out your handy dandy calculator. we're going to do 42 times 2 divided by 9.81, and then don't forget to square that result. And I get my time to be 2.93 seconds. Sorry, I'm not being good with significant figures there, but this is just our example. Okay, so that's how long the ball is in the air. Next question. How far does the ball go? So if I want to know how far the ball goes, how far out from the building that it lands, that's the horizontal distance. I want to know this piece of information here. Well, once again, actually, I can use that exact same equation. Delta x is v naught t plus 1/2 a t squared. But in this case, I know my x acceleration is 0. It's just v naught times t. I know the time now, and I know v naught, the velocity in the horizontal direction, is 32 meters per second. The time is 2.93 seconds. And so I take those, multiply them together, and I get 94 meters. So it looks like this would land 94 meters from the building. The last question that you could be asked is, how fast does it hit the ground at? Now, this is a tricky question because some people want to think, oh, well, it's going to be 0. The final velocity is going to be 0, right? And that's true after it hits the ground, but we're more curious with what it is right before it hits the ground. That determines how, injured the ball is going to be once it actually hits that ground. So how fast is it going when it gets there? Well, one thing to think about is that there's no acceleration in the x direction. So how fast is it going to be going in the x direction? Well, its x velocity is not changing. So how fast it hits the ground at in the x direction is 32 meters per second. But it is changing speed in the y direction. So we know that's going to be 32, but I can figure out how fast it's going in the y direction. Remember that v equals v naught plus a times t. So I know that I'll take the initial velocity in the y direction, 0, and add 9.81 times the time, 2.93. I'm going to label this with a y. So my velocity in the y direction is simply 9.81 times 2.93. And I end up getting 28.7 meters per second. 28.7 goes there. Now, is that the total answer to how fast? Well, remember, velocity is a vector. So yes, that is one answer. We can say it's going 32 meters per second in the x direction and 28.7 in the y direction. Or if you wanted to find the total speed, you would need to find the magnitude of the velocity vector. And if you have two components, how do you find the magnitude of the total? Pythagorean theorem. But we'll save that for another time. Okay, that's horizontal projectiles. But now we're going to go ahead and take a look at what do I do when I have something projected in a vertical direction as well. So this is a really common scenario that happens, especially in sports ball. A soccer player here kicks a ball with a speed of 13 meters per second at an angle of 34 degrees above the horizontal. There's, again, many questions we can ask. But first, let's make a little diagram of my scenario, because I now need to deal with the fact that my initial velocity is a vector. It is moving 13 meters per second at an angle of 34 degrees above the x direction. And the first thing you should always do in a vertical projectile motion problem is split this initial velocity up into an x and a y component. So you might remember doing this when we talked about vectors. Going to use some trigonometry here for my velocity in the x direction, since that's the adjacent side of this triangle. It's just going to be 13 meters per second times the cosine of my angle. So cosine of 34 degrees. Do that in your handy dandy calculator. 13 times cosine 34 is, and I am not in degree mode, so make sure that your calculator is in degree mode when you try it. I get 10.8 meters per second. In the y direction then, I could do Vy. It's going to be the hypotenuse again. But now, since this is the opposite angle, times the sine of 34 degrees. So 13 times the sine of 34 is about 7.3 3 meters per second, which makes sense because if it's at 34 degrees, it should be going more in the x than it is in the y. Okay, so I've got my two components of my initial velocity vector. Now we can solve this problem very similar to the one that we just did. I like to set up, once again, and this is not something you have to do, I like to set up one of those projectile motion charts where I'm going to list out, distance, and then initial velocity, final velocity, acceleration, and time, and we'll keep track of the x and the y components. So let's ask some similar questions. Question 1 is how far, or how long. We'll say how long first. So how long is our ball going to be in the air? So I want to know the total time. So filling out our information, we knew the initial velocities in the x and the y. We said that the x initial velocity was 10.8. We said the y initial velocity was 7.3. I also still know the acceleration due to gravity, right? It's 0 in the x, and it is 9.81 in the y. But I do need to be careful about direction here, because I'm kicking my soccer ball upward, and it's going to be going in kind of an arcing path like this. But if my initial velocity is upward, what direction is my acceleration? It is downward. And so in this case, I need to keep track of the fact that the initial velocity is in the different direction than the acceleration. So I'm going to call the y up positive, and so we'll say that the initial velocity is positive in the up direction, and then the acceleration is negative, so it's going in the downward direction there. This is all the information that I've been given. And if you look at the equations that you have, this is not enough to solve for anything. So there must be something else that we need in order to figure this out. And there's a couple ways you could do it, but I find the easiest way to be to think about the problem. If I look at this path here, is there a place in this path where I know something else? And that place actually is right here at the top, at the very top of the soccer ball's motion. I know the y velocity. At the very top, there has to be a point where it is no longer going up, but has not yet started falling down, where the y velocity is 0. So I'm going to split the problem in half. So I'm going to call this the table for at the top. And at the top, the initial or the final y velocity is 0. Now I have enough information to solve for the time. I can use the equation that v final is v plus, or v naught plus a times t. The final velocity at the top is 0. That equals the initial velocity, 7.3, minus 9.81 times the time. And now you can see why that minus is important, because otherwise this mathematically wouldn't work out. And you end up taking 7.3, dividing by 9.81, and I get the time. And I'm going to call this t1 half to be 0.74 seconds. So that's my time to the top. Now, what if they asked you, how long does it take in total? Well, I have solved to get to the top, and everyone knows from kindergarten science that what goes up must come down. If that's the time to get to the top, I called it t1 half because that's just half of the time. To double it is what you get to the whole flight time. So we'll say that the total time is just twice the half time. So 2 times 0.74 seconds is my total time. Doubling it, I could have done that in my head. I get 1.48 seconds. So that's my time of flight. Something else they could ask you is, how far does it go? Now, there's a couple ways that you could solve this out. You could either say, okay, let's figure out what's the distance from here to there to the top, and you would use the 0.74 seconds, or I know the total time, so I could just use the total time for this. I know that my change in position is going to be equal to the initial velocity times the time, plus 1/2 times the acceleration times the time squared, and I could figure out how far it's going to go. Now, remember that in the x direction, the initial velocity, or the acceleration, is 0. So all I need to plug in is my initial velocity, 10.8 meters per second, times the time, 1.48 seconds, and I get an answer of, looks like 15 or 16.0 meters. So pretty good soccer player here. Lastly, you could also ask, well, how far up does it go? What's the vertical height that my thing reaches? So this is my change in the x, but I could ask, and I'll call it change in the y, what's the vertical height? Well, we're going to use the same equation, except now we have the v naught being 7.3 for my y direction, so 7.3. The time to get to the top was 0.74 seconds. Then it's plus 1/2 times negative 9.81 meters per second squared times the time, which was 0.74 squared. Now I'm using the half time, the 0.74, because if I want to know how far up it goes, I need to find that right at the place where it reaches the top. If you plugged in the 1.48, you'd find the change in y would be 0, which makes sense, because once it gets to the end, it is exactly at the height that it left the ground at. So we plug this in our calculator. 7.3 times 0.74 plus 1/2 times negative 9.81, so that'll end up being subtracted, and then times 0.74 squared, and I end up getting, looks like the change in the y, so the how high to the top is 2.7 meters. Okay, last thing I wanted to mention about vertical projectile motion is that there's an ideal angle to launch something at to extend the range. There's a formula you could use to calculate range if you go look up some things online, but I don't need you guys to worry too much about that, because this process will work always. But you can almost imagine that if you want to have something go the furthest you possibly could, that maximum angle, or the angle for maximum range, is going to end up being 45 degrees, exactly in between vertically upward and horizontal, because that's where you have the maximum horizontal component and vertical component of your velocity. So that's what's going to give you the best range. But air resistance will change that. If you turn on air resistance and start considering that, your ball will not fly as far or as long and not reach as high. Okay, folks, thank you guys so much for watching. Hope for projectile motion is making sense. Have a fantastic rest of your day.